So let's talk about a resource-efficient delta update algorithm for usually deeply embedded devices, but not limited to that. Can do a Linux system update there as well. So what does it mean, resource efficient? Well, we mean we can do an update with only 30% or even less additional flash. It obviously depends a bit because it's delta on the size of your firmware or more on the change you have done. And the data you have to send therefore is obviously also reduced a lot. But it's still fully power loss protected, so you can switch off your unit whenever you want. It will restart, it's never bricked. And there's also possibility to do rollbacks. So let's think about a bit of the traditional way. We have on the left side, we have kind of the microcontroller with the internal flash. And there is on the bottom, there is a flash loader, bootloader, however we call it. And there is a firmware. And obviously you need some empty space to put the update in. So usually there is a firmware which gets some header, and then it's getting transferred to the upper part of the flash. And then the bootloader gets activated, which does erase the old one and copy the new one over to that part. And then it's activating the new one. And from now on, the new one is kind of running. Okay. With this way, rollback is really possible because you can swap those things. Essentially, you need a bit of the spare thing to do that, but you can roll back. It's obviously also power loss safe because you can always restart. But it obviously needs double the flash size. Okay, let's enhance that with compression. We do exactly the same thing, but the firmware is now compressed. Put it on top. And the bootloader now needs to have the possibility to do a decompression. Erases. Now do a decompression. And we have the same done. It's a faster transfer, obviously. We need less flash. Or we can add bigger firmware, as we see in this example. We need a bit more resources in the bootloader for the zipper. But rollback is not really easy. Well, you can do if you do compress and not only decompress, but it's not that easy than a decompression. Okay, now let's talk about delta update, what we want to do. What we need to do to have a delta update, we rely on those bytes which are already in the old and the new byte in the new image in there. We keep them, we don't have to transfer them. So we create a diff between the old, which we know it's on the target, and the new one, create a delta file, and send this delta file over to the embedded device with the knowledge of the old file. We can now, with the patch file, create the new file. So far so good, that's fine. Obviously the left part is done in engineering. When you have a new version, you create a diff to the old version or versions. There's probably more than one out there. And this has to be done in the embedded device. Okay, I was taking a look into the BSDiff algorithm and I didn't care about creating the diff. I only cared about the patch algorithm because creating I can directly use the BSDiff. So the delta file looks like this. There is obviously header and then we have three blocks. There's a control block, diff data block, and extra data block. All are compressed with BZ2, but essentially it could also be done with a different compression algorithm. We can kind of modify that. And then we unzip the control blocks, and each control block has a add block length, extra data length, and a seek offset. What does it mean? Okay, the add block means take the diff data and do a byte-wise plus operation without overflow and read with the data which gets read from the old version of the data. And then write this to the new one. Kind of a bit like a stream operation. So you fill in the new version with every byte then. And then the second part is the extra data. This is not mixed with the old version, so that's kind of really new data. just decompress and write to the binary data. And then the last one is the seek operation. So for the read pointer, you can now place the read pointer for the next block on a different position. So that's the complete algorithm, patch algorithm. So this is really 200 lines of C code. It's really not complicated. Obviously you need a decompressor. That's essential, because otherwise the diff data had a lot of zeros. And the only effect is if you do them compressed, you really save a lot of space. Okay, so now the first idea I had was, okay, I take the small Delta file, put it to the device application. I usually distinguish between the application and the flash loader. I update the device application, but never the flash loader. And now we apply the patch by reading firmware version 1 and writing to firmware version 2. This is a way which is obviously working. No problem on that, but still double the flash size required. This is something you can see often in many solutions. Okay, what if we do the patching by the bootloader? So the application writes the Delta file on the top of it, and the bootloader now starts patching. Okay, he reads the Delta file, and he reads the originally binary version of it, Delta file and the binary version, and then it writes to, well, can only be write to that application data here. But that overrides part, which, remember, on the seek operation, might be used by the patch in a later stage. And even worse, what about power loss in between? Where shall I start again? And what is the data which is already overwritten there? So the problem is really overriding the old data by reading them. Okay, the idea would be to split the firmware and add a buffer. So we now split the firmware, and rather than overriding that old file here, we are writing into a buffer. And after this, for this part is done, then we override the part 1 here in that flash sector. And now we can go to the second part and say, okay, create a Delta file from this remaining part, write it to the buffer, and override the second, and so on. Buffer size can obviously be different. The smallest one is usually the flash sector size. It gets a bit less efficient the smaller the buffer gets. But then the question still arises, what happens on power loss? So let's assume we are doing the first step. If we have a power loss now, nothing would happen. We will just restart again. Okay, now we're overriding the binary version, the old version from the buffer. If now we got a power loss, we restart again. So let's assume we're restarting again, doing the same thing again, but now the patch algorithm to create that buffer relies on this part, and this part is already overwritten. So that does not work. The solution here is that we don't do destructive actions upon restart. So we kind of build transactions here. We'll explain that. So what we have now is we have the bootloader, we have the old version in there, we have the buffer which we need to persist in between, and then we have small Delta files. They are usually even smaller, but because of the letter size I don't want to make them very small. And the patch algorithm works now like that. So this is the green box is essentially the update file. So we do the first patch. And the first patch, you can also see the patch is the reverse from the diff. So the first diff was created by taking the complete old file and compare it with the small part of the version 2. So we take the patch, have access to the complete old version, and write it to the buffer. And now we mark this step as done. So this transaction is done, which means on a reboot, on a power loss, this step will not be taken, will not be done anymore. And now we're starting overriding this one. That's why we need this flag to make sure that if we override this one here, we will never read this one from the first delta again. That's why it's important that we don't do the first step anymore on a power loss. Okay, we're obviously marking this as well for the same reason. And then we do the same with the delta file 2. So we read the patch file here, merge it with the old data, which is now smaller. We don't have the complete old data available anymore. So the diff gets a little less efficient, but usually the memory layouts are not changing too much. If the flash layout would change radically, this would cause a problem. And then we write to the buffer. Well, set the transaction flag here and above somewhere. Copy the buffer to the part 2. Then we do the marking again, the transaction buffer, patch the third delta in the buffer, mark it, copy it to that part, and we're finally done. Well, if you see, this one is there. It's kind of an instruction list, so it's kind of pretty easy to build. So we do a patch from D1 plus address 1 onto address 1. Then we set transaction bit 0. Then we do a copy operation, and this is something which repeats. So this is kind of a bit of an instruction list. So kind of looks like a machine code. So could be kind of a, I don't know, very, very small VM or so. So what do we get now? Well, I tested on one of our tools. They usually have minor changes, so there's no changes in the field, and there was no feature added. It was just bug fixing and some small things, no big feature adding. So what we see is it's a table which you make a delta update between 110 and 120, and the delta file you get. So you remember the 3 delta files on top, so everything which is in the green box is now 1% of the original file size. So the firmware size was 1.3 megabyte, and at the end this one was roughly 13K. At some point in time there was a bigger change because there was a bigger hardware change. So the driver also has to change quite something. So there we had a bit more. Okay, so what does it mean? So this one is usually what you take when you install on each update on a device. Obviously, if you didn't update for a long time on your device and you're still on the very old one, and 5 years later you want to update to the latest and greatest, then this one gets bigger. If you don't have that space, you can still say, okay, I update to this one, and then I can make this step from here to this one, which is already smaller. Or do even more intermediate step to update to this one, and then I take this one, the difference to this one here. It's only 3 anymore. So it could be still fit in if it's not possible. So if we get a bit of a feeling what that means, we have the big application, we have the bootloader, and this is kind of the sizes kind of match. We need a buffer. It depends very much on also the flash layout. In this case, the sector size was 128K, so that was really big. So we need to have one buffer of 128K because this always have to be a sector size as a minimum. But still the update doesn't have to consume that much. Obviously also we need a space for 128K because otherwise we will delete the buffer also. That would not work. So that was pretty efficient so far. So the additional space we need is really small, and even a buffer could be reused for something else because it's only required while updating. rollback. Well, as in the very first example where we just have two partitions, we can swap the partitions back and forth. That's obviously something we can't do. But what we can do is, when we do an update, we usually have in the update file the data file which stores the difference between version 1 and version 2. And that's what we use in update. So after this delta file is executed, we have now the complete correct version 2. Well, what if we also store, in case this is broken, we want to go back to version 1. Well, if we store the reverse delta file also, then, because the flash here is always correct, it's just the source code was probably wrong. Functionality was wrong. It's not that we have incorrect flash cells. If we have broken flash cells, we can't solve that. With none of that functionalities. Also with the first one, where swapping two partitions wouldn't help. But what we can do is we really store the reverse delta file here as well. Should be probably about the same size. And if this kind of the sanity check on startup signals to the bootloader, oops, it's not really working, then the bootloader will just trigger the second step in the update file and execute it exactly the same way as the first one, because it's just, yeah, now having the content is the delta between the version 2, which is stored, and the version 1, which we want to have. Okay, thanks for listening. That's it.